Hi guys! Today we are going to discuss some example problems for fluid mechanics. For the first problem, let's start with the density. The problem is you purchase a rectangular piece of metal that has dimensions of 5 by 15 by 30 millimeters and mass of 0.0158 kilogram. The seller tells you that the metal is gold. To check this, you compute the average density of the piece. And what value do you get? Were you cheated? So, first, let's recall the formula for density, and that is density raw equals mass over volume, where the density of gold is equal to 19.3 times 10 to the 3 kilogram per cubic meter. So for the given, let's start with the dimensions, and that is 5 by 15 by 30 millimeters, and that is the volume. Next is the where the volume is calculated by 5 times 15 by 30 millimeters, and that is equal to 2,250 cubic millimeter. And since this is a cubic millimeter, we need to convert this into meters, and that is equal to 2.25 times 10 to the negative 6 cubic meter. For the mass, that is equal to 0.0158 kilogram. So let's try to solve this. So let's solve for the density, raw, mass over volume. So here, we need to substitute the values for mass over volume here, and that is equal to 0.0158 kilogram over the volume, and that is 2.25 times 10 to the negative 6 cubic meter. And this is equal to 7,022.22 kilogram per cubic meter. And that is the average density of the piece that you purchased. And if you compare this with the density of gold, and that is 19.3 times 10 to the 3 kilogram per cubic meter, we can say that the metal is not a pure gold. And imagine, this is only around 36% that of gold. So, meaning you are not really buying that real gold. For the second problem, we are going to deal with the pressure in a fluid. So, our problem, a closed container is partially filled with water. Initially, the air above the water is at atmospheric pressure, and that is equal to 1.01 times 10 to the 5 Pascal. And the gauge pressure at the bottom of the water is 2,500 Pascal. Then, additional air is pumped in, increasing the pressure of the air above the water by 1,500 Pascal. So, we need to find letter A, what is the gauge pressure at the bottom of the water? For letter B, by how much must the water level in the container be reduced? By drawing some water out through a valve at the bottom of the container to return the gauge pressure at the bottom of the water to its original value of 2,500 Pascal. The pressure of the air above the water is maintained at 1,500 Pascal above atmospheric pressure. So let's start with the given. And the given for the atmospheric pressure is 1.01 times 10 to the 5 Pascal. Next is the gauge pressure. And the gauge pressure from the formula of the pressure in a fluid, and that is given by the P minus P air, and that is equal to 2,500 Pascal. So the P here, this is the pressure at the bottom, and here the P air is the pressure at the surface of the water. Next is the additional pressure that is being pumped and it increases the pressure. So and that is equal to 1,500 Pascal. So here, we need to find the gauge pressure at the bottom, and for letter B, the height. So for the solution, uh, since the pressure difference between the surface of the water and the bottom is due to the weight of the water, and this is equal to the gauge pressure, and that is 2,500 Pascal. So even after the pressure increases above the surface, but the surface pressure increases, the surface pressure increase of 1,500 is also transmitted to the fluid, making the total difference from the atmospheric pressure to be 2,500 Pascal plus 1,500 Pascal, and with a total of 4,000 Pascal. So that is the gauge pressure at the bottom. For letter B, we need to find the height. So let's apply this formula. The pressure at a certain depth or at a certain height is equal to the atmospheric pressure plus rho gh, where rho is the density, g is the acceleration due to gravity, and h is the height. So here, we are going to use the P minus P naught, or the atmospheric pressure, to be the gauge, and that is 2,500 Pascal. And this 2,500 Pascal is equal to rho GH from the formula, from this formula. Okay, so where rho here is the rho for the water, and that is equal to 1,000 kilogram per cubic meter. And since we need to find the height here, so by manipulating this formula here, we can find the height as 2,500 Newton per square meter over 1,000 kilogram. This one, the rho, kilogram per cubic meter, the g, 9.8 meter per second squared, and that is equal to 0.255 meters. And that is the height. Okay, so to keep the bottom gauge pressure at 2,500 Pascal, after the 1,500 Pascal increase at the surface, the pressure due to the water's weight must be reduced to 1,000 Pascal. And we need to compute for the new height. The new height is given by this: 1,000 Newton per square meter over 1,000 kilogram per cubic meter times 9.8 meter per second squared, and that is equal to 0.102 meters. Thus, the water must be lowered by these values: 0.255 meters minus 0.102 meters, and that is equal to 0.153 meters. And here, at height 0.0153, this is the height where we have the additional pressure of 1,500 Pascal. The next problem is about buoyancy. So our problem, a rock with density of 1,200 kilogram per cubic meter is suspended from the lower end of a light string. When the rock is in the air, the tension in the string is 28 newtons. What is the tension in the string when the rock is totally immersed in a liquid with density of 750 kilogram per cubic meter? So let's start with the given, and the density of the rock is equal to 1,200 kilogram per cubic meter, and the density of the liquid is 750 kilogram per cubic meter. And we also have the tension in the air that is equal to 28 newtons. And here, for this problem, we need to find the tension in the string in the liquid. Okay? So here, we have to recall the equation of the buoyant force, and that is equal to the density times the volume times the gravity. or the acceleration due to gravity, where the density is equal to mass over volume. And m is mass, v is the volume, and g is the acceleration due to gravity. So in air, in the air, we have these forces. We have the tension in the air, and that is the upward force, and the weight, and that is equal to mass times gravity. So we can have this equation: tension in the air is equal to the weight, and that is equal to mass times gravity. Okay, so in terms of density, since all the given here is in terms of density, so we can write as tension in the air is equal to here density times volume. So we just cross multiply here. So mass is equal to rho times the volume times the gravity. And here we can have the volume to be tension in the air over the rho times the gravity. So we just manipulate this equation. And this is equal to 28 newtons over the density 1,200 kilogram times the 9.8 meter per second squared. And this is equal to 0.00238 cubic meter. And for the liquid, so here we have the forces, the tension that is upward, the buoyant force that is also upward, and the weight minus weight. So we just transpose this to other side. So we have this equation. And the tension is equal to mg minus the buoyant force. So we transpose the buoyant force to the other side, or the other side of the equation, and we have the rho times the volume times gravity. So this is for the here mg. So can you recall here? So mass is equal to rho times the volume minus the density. So our buoyant force is equal to this one. Okay? So the density of the liquid times the volume times the gravity. Okay? So we need to find the tension in the liquid. Okay? So we can manipulate this equation. So we have Vg times the rho of 1,200 minus the rho of the liquid. And this is equal to the volume, that is 0.00238 cubic meter times 9.8 meter per second squared, and times the difference of 1,200 minus the 750. So this is the density of the rock, and this is the density of the liquid. So the tension in the liquid is equal to 10.5 newtons. So for the next problem, we will deal about the fluid flow. You need to extend a 2.5-inch diameter pipe, but you have only a 1-inch diameter pipe on hand. You make a fitting to connect these pipes end to end. If the water is flowing at 6 cm per second in the wide pipe, how fast will it be flowing through the narrow one? So the given is the D1, that is 2.5 inch. For the volume, or the velocity, velocity of the wide pipe, we have the 6 cm per second. And for the D2, that is the diameter of the smaller pipe, and we have 1 inch. And for this problem, we need to find the velocity of the narrow pipe. And remember, what you have learned is that when you narrow the width of the pipe, it will increase the speed of the flow of the fluid. Okay, so we need to set up the continuity equation. Here we have the area 1 times the velocity 1 equals the area 2 times the velocity 2. And the area for the pipe is given by pi over 4 times d squared, where d is the diameter of the pipe. Okay, so the equation becomes the pi over 4 times d1 squared times v1 is equal to pi over 4 pi d2 squared times the velocity 2. Okay, so cancel the pi over 4 because they are on the both sides of the equation. So we can find the velocity 2 or the velocity of the smaller pipe to be d1 over d2 squared. So you have to this one transfer these to here. So we have d1 over d2 squared times the velocity 1. And substituting the values, we can have the 2.5 inch over 1 inch, so cancel, and squared times the 6 centimeter per second. And we can have the velocity of the narrow pipe to be 37.5 centimeter per second. So for you to achieve the same volume flow rate, the water flows faster in the smaller diameter pipe. And remember that the pipe diameters entered in a ratio so that there was no need to convert units. For the last problem, we have the Bernoulli's equation. So the problem, a sealed tank containing seawater to a height of 11 meters also contains air above the water at a gauge pressure of 3 atm. Water flows out from the bottom through a small hole. How fast is this water moving? So, in this problem, we need to draw first the figure. Okay, so we have a tank that is sealed, which contains seawater and which has a height of 11 meters. So we can have this y1 and the bottom part is the y2. And we can set y2 to be 0. Okay, and also the gauge pressure here, meaning the gauge pressure is we have the 3 atm. So here, this is sealed and also the water flows out from the bottom. Okay, so this is a small hole and we need to find the velocity of the water that is moving out at this hole. Okay, so here we need to apply the Bernoulli's equation. So for points 1 and 2 as shown in this figure. Okay, so here we need to find again the velocity at this point, meaning at point 2. Okay, so the Bernoulli's equation is given by is here again where y1 is equal to 11 meters and y2 is 0 as what I have said earlier. Okay, and we need to find the velocity at point 2. So here, the Bernoulli's equation is given by P1 plus rho gy1 plus 1 half rho v1 squared is equal to P2 plus rho gy2 plus 1 half rho v squared 2. Okay, so this is the Bernoulli's equation. And from the continuity equation, we have the A1 V1 is equal to A2 V2. Okay, so continuity equation, and A1 here is the cross-sectional area of the tank A1. Tank 1, cross-sectional area of tank here at point 1. And as you can see here, the A1, the cross-sectional area of tank at point 1 is much greater than the cross-sectional area of the hole. Okay? So we can conclude here that the velocity at 1 is much less than the velocity at 2. Okay? So we can say that the term for the 1/2 rho v1 squared, okay, here this term can be neglected. So we can neglect this and we can set this to 0. Okay, so let's execute. So here we have the P1 here, rho plus rho gy1. So we disregarded this term. P2 plus rho gy2 plus 1/2 rho v2 squared. Okay, so again, we need to find the velocity at point 2. Okay, so 1/2 rho v2 squared. So we manipulate this equation and we can get this as P1 minus P2. Okay, this one plus rho g times the y1 minus y2. And again, y2 is 0 because this is at the bottom. Okay? And v2 here is equal to this one. So transpose this, so become this one times 2. Times 2 of this term. So 2 times this term p1 minus p2 plus rho gy1 over rho. So we can find the v2, the square root of this whole term. Okay? And since p2, so p2 is equal to pa. Okay? So here, so the pressure here is equal to the atmospheric pressure. Okay? And we can say that, and also since the P1 minus PA here is equal to 3 atm. Okay, so P sub 0 here is the atmospheric pressure. So we can we can also say that this is PA. Okay, and V2, substituting these conditions, so the 2 times P1 minus PA over rho plus 2 gy1, so rho over rho, so we cancel that out, and this whole term is the square root. Okay, so P1 minus PA is again 3 atm. So substitute these values and that is equal to 3.039 times 10 to the 5 Pascal. And the density of seawater is 1030 kilogram per cubic meter. So substituting all these values, we can get the velocity at point 2 to be 2 times 3.039 times 10 to the 5 Pascal over the 1030 plus 2 times 9.8 times 11, and that is equal to 28.4 meter per second. Okay? So, this is what we've got. And the velocity of the water that is moving out from the small hole is equal to 28.4 meter per second.